All right, we're going to start talking about inverse functions. So we have talked about functions a lot of times as a box, right? Or a function machine. You put in an x and out comes a y. Okay. Well, the question we have is, can it run the other way? Can you turn it upside down? Can you put in a y value and get out an x? Okay. Sometimes yes, sometimes no. So here's this idea of a time that we might use functions. We've got a weather forecast, but it's all in Celsius. And maybe it's like your grandma, so she doesn't know how to change the settings on her browser or something on the web page to show it to her in Fahrenheit. So, but she's really good at math. And so she decides to take these values. She knows the relationship between Fahrenheit and Celsius. So she knows she can put in, she knows this equation, 5/9 times the Fahrenheit temperature minus 32 will give her the Celsius temperature. Well, she knows the Celsius and she wants to find the Fahrenheit, but she's very good at algebra. So she uses this relationship and she plugs in the Celsius value of 26, and then she multiplies by 9/5 and then adds 32. And she says, okay, if the Celsius temperature is 26, the Fahrenheit temperature is 79. And she could do that for each of her temperatures here. She could plug in the Celsius value and then do the algebra to get her Fahrenheit value. But it seems like there should be an easier way, right? There should be a way that you could have, if we thought of this as the function, that there should be the inverse function where she could just plug in the Celsius temperature and without having to do a bunch of rearranging, out would come the Fahrenheit, right? She has a function that goes one way and she wants to go the other way. She wants the inverse. All right, so here's the definition of the inverse of a function. So for any one-to-one function, f of x equals y, a function f inverse of x is an inverse function of f if f inverse of y equals x. Okay, this can also be written as f inverse of f of x equals x for all x in the domain. It also follows that if f of f inverse of x equals x for all x in the domain of f inverse, if f inverse is the inverse of f. Blah, blah, blah. That was a lot of words. Okay, so what does that mean? Does this look familiar? We've got one function on the outside, one function on the inside. Looks like those are being composed with each other, right? If you can compose two functions together and the output of that composition is x, you've got inverses, okay? And it can go in either order. F composed with f inverse of x, if that equals x for all x, you've got an inverse, okay? So something a little bit tricky about this notation, okay? It has a -1 in the exponent. We say this f inverse, okay? This is very important. This is not the case. F inverse, in this case, this notation does not mean that this is the same as 1 over f of x, okay? This doesn't say like put it in the denominator as if it was, x to the -2 in some expression where we could put that in the denominator. So it is confusing notation. And it would make sense that this would be the case, but it is not. Okay, this notation for f inverse just is the notation. It does not mean this. Okay, something else to notice is not all functions have inverses. Okay, so we'll talk about some that don't have inverses. And one other thing I want to talk about, right here at the beginning, it says for any one-to-one function. Okay, well, let's think about what a one-to-one function means, right? A one-to-one function means that for every input, there's only one output, right? Why would that be important? Let's keep thinking about that. In order for something to be a function, for every output, for every input, there can only be one output, right? Well, we're kind of going the other direction, right? And we want the other direction to also be a function, okay? So in order for a function to have an inverse, it has to be one-to-one. Okay, that's an important idea. Okay, so for example, we've got one function, y equals 4x, and another function y equals 1/4 x. They are inverse functions, and let's show it. If we compose them together, f inverse composed with f of x equals f inverse of f of x, right, which is 4x. So we plug that in. Look, I guess we're calling this f of x and this f inverse. It's kind of confusing notation that they used y both there. But we plug 4x into this function here, and out pops x. Okay? Or we could do it the other direction, f composed with f inverse. F of 1/4 of x, we plug 1/4 of x into this equation, we get 4 times 1/4 x, and out pops x. So, yep, these are inverses. Okay? All right, so let's think about inputs and outputs for a minute. So we've got a particular one-to-one function, f, and we know if we put in 2, out pops 4, and if we put in 5, out pops 12. And let's say we know it has an inverse, f inverse. What two function statements can we make about f inverse? Well, the inverse, the input of f gives us this output. This input gives us this output. The inputs and outputs are going to switch, right? It's like we're going from Fahrenheit to Celsius, and now we're going to go from Celsius to Fahrenheit, right? The inputs and outputs switch. So we could say this a few different ways. If f of 2 is 4, then f inverse of 4 is 2, right? If f of 5 is 12, then f inverse of 12 is 5, right? The inputs and outputs switch. And if we wanted to call, instead of f inverse, we could call it g. We could say f and g are inverses. So we could say g of 4 is 2 and g of 12 is 5. So let's just look at what that looks like as input-output pairs. Inputs 2, outputs 4, inputs 4, outputs 2, right? They switch. 5, 12, 12, 5. Remember that, because in a minute we're going to talk about graphs, and it looks like the x becomes the y, and the y becomes the x, right? Okay. All right, so suppose we have these two functions, f of x equals 1 over x plus 2, and g of x equals this thing, 1 over x minus 2, and they ask us, are they inverses? You could pause this video and test that out. Well, let's look. We could say g of f of x, right? We're going to say compose them together, g of f of x. So let's see, that would be f of x, this whole expression, we're plugging into g. So this whole expression is getting plugged in for that x. Okay, that's what we've done here. All right, now I've got to algebraically simplify this. 1 over x plus 2 is the same thing as just x plus 2, right? If we invert and multiply this denominator, or we could multiply top and bottom by x plus 2. X plus 2 minus 2, those cancel out, and we just get x. That is enough to show that they're inverses, but we could also do it the other way, f of g of x. Well, okay, g of x, we're going to put this whole thing into f of x, so everywhere there's an x, we're going to put this whole thing. So we get 1 over that whole thing, g of x, plus 2. 2's canceled, 1 over x, could multiply top and bottom by x and get x. Yes, we compose them either direction, out pops x. We're good. These are inverses. So we could say g is f inverse, and f is g inverse. Okay, they are inverses of each other. Here's another one. If f of x is x cubed, and g of x is 1/3 x, are they inverses? You could pause and check it out. Well, f of g of x, so we're going to put 1/3 x in to this function, is going to give us 1/3 x, the whole thing cubed, which is going to be x cubed over 27. Is that the same thing as x? It is not. Okay, so these are not inverses. Okay, so we've kind of mentioned this a few times. The domain and the range, the inputs become the outputs and the outputs become the inputs. So a precise way to say that is the domain of f is the range of f inverse. And the range of f inverse is the domain of f inverse. Sorry, the range of f is the domain of f inverse. Right? F of x goes from here to here. F inverse goes from here to here, right? Maybe this is Fahrenheit and Celsius, Celsius to Fahrenheit, right? The domain and the range of F is the range of F inverse. Okay, so the domain and range switch. So, given a function, find the domain and range of its inverse. How do you do it? Well, if the function is one-to-one, write the range of the original function as the domain of the inverse, and write the domain of the original as the range of the inverse. Pretty easy, okay? But if the domain of the original function needs to be restricted to make it one-to-one, then this restricted domain becomes the range of the inverse. What does that mean? Okay, well, let's look at some toolkit functions. Let's look at absolute value or reciprocal square, so 1 over x squared. Are these one-to-one functions? No, right? For one output like 3, if I said what input gives you, solve this, f of x equals 3, well, you're going to get 2 answers, 3 and negative 3, right? Or same thing over here, except like what about, if I said solve f of x equals 1, well, 1 and negative 1, okay? So you can see how that could be a problem going the other way, right? So really going the other way is like solving it, like setting it equal to a value, right? So what do we do about that? Well, we restrict the range. So we restrict the domain of the original function. We say, well, we need this to be one-to-one. We need this to pass the horizontal line test. And it doesn't. But what if we just ignored this part of the graph? What if we just looked at all these values 0 and up? Is that function one-to-one? Or over here, what if we said, let's just ignore this half of the graph. Let's just look at all the x values greater than 0. Is that one-to-one? Yes. Okay, so we can do that. I mean, we have to be explicit about what we're doing. We have to state what we're doing. But we can say the absolute value function does not have an inverse because it's not one-to-one. However, on the restricted domain from 0 to infinity, it does have an inverse because that is one-to-one. So on the range of my inverse function will be 0 to infinity, right? Or over here, same thing, 0 to infinity, except not including 0 because it's not defined there. Okay, so yeah, that's the last slide for this section. So we will talk about how to, so far we've been given functions and said, are they inverses? Now in the next section, we will figure out what the inverses are.